here in this is I think the third video of my non-mathematical introduction to quantum computing. Here we're going to talk just only about one gate, which is the H gate, the Hadamard gate. So we talked about the X, Y, and Z gates, the R rotation, X rotation, Y rotation, Z gates, S and T, like all that stuff that help you understand how you manipulate information in within a qubit. Now the Hadamard gate is a bit of a special one because what it does is just with one gate it creates that type of uncertainty that like you're halfway 0 and 1. So when you apply to 0, right, basically it gives you 50% chances of seeing 0 and 1. Now you say, how is that anyhow different or than just applying like a rotation, the rotations here, right? So I think it was rotation Y. Was it rotation Y? Exactly, right? So, and it's different in the sense that, so actually, I don't know. Let me check something. If I do this and I do a rotation Y, okay, it's kind of, because this is, it's a different effect. So what I want to show is the fact that the Hadamard has an interesting effect when when you apply Hadamard to a gate with to a qubit in the 0 state, it creates this. This is the superposition of 0 and 1, 50-50%. But if you apply that on sort of a qubit with an amplitude 1, it doesn't have to be 100% 1, but this helps you. So as long as there's a bit of 1 in there. What it does is, for this case, you can see it just actually creates the same effect. So it's from a measurement probability perspective, is 50-50, but the one component is basically has a negative phase, so it's yellow. And this is why this is important. This is important because the Hadamard gate is the gate that's gonna help us create superpositions in a really quick way. So if I I know that I shouldn't be doing this right now at this point in the tutorials, but if you add 2 qubits and you apply, so now you have a state 0, 0, and now you apply Hadamard gate in each qubit, then you get into, now with 2 qubits you're able to represent the 4 possible values all at once with equal probability. So this is basically, if you go to the measurement probabilities, you have 25% chances of measuring any of those states. And I think that's what most of the computations and most of the algorithms and things you can do with quantum computing that are not the same like in classical computing start with this. Basically, you create a superposition and then you do programming on the superposition amplitudes or on the superposition phases, because basically if you can now flip the sign of some of them, the phase basically, then you literally have encoded something you have something encoded with a phase, so to say, right? You have like a 0, 0, 1, 1, if you want to, depends on how you map that, but you basically encode information also on the phases, right? So, but we'll talk about this later in another video. Let's go back to 1 qubit. So that's basically what the Hadamard gate allows you to do. So the Hadamard gate basically allows you to create that uncertainty. Now, what happens? The interesting thing is what happens when you apply Hadamard in other qubits which are not in 0 and 1, right? So what if we say, what happens if we apply it to a qubit that is in this state, for example? I don't know. I actually don't know. Haven't tried that. So it's a 1, but it's not a negative phase. It has like a complex phase. If I apply Hadamard, what's going to happen? Yeah. So you create a complex superposition or sort of complex uncertainty. I don't know how. I don't know if that's sensitive or sense, like something that makes sense to say in this way. But basically, it so you definitely have to play with that a lot. So to kind of understand what are the effects in here. So it's creating this superposition. If you do this, on a qubit that's minus, so that's 1. Oh, come on. That's in the 1 and negative phase, right? So it's going to give you that, which is the opposite of what you get when you apply simply a Hadamard with 1. And kind of the reason is, you can think of it like when you apply a Hadamard on a 1, it kind of negates the phase. But if what you had was already a negated phase, I mean, that minus and another minus will turn it into a plus. So, I mean, that's a bit of mathematics, but I don't think you should complain about this. So you see the arithmetic is happening here, right? So it actually makes sense. So because this was already in a minus, the phase is already minus, when you add a Hadamard, which would create a negative phase for your amplitude of the 1 component, it will now turn it into a positive one. And the 0 one, which would otherwise be positive, becomes negative. So here's where you can see that the effects of using the Hadamard gate and later on with more qubits is that certain amplitudes will cancel out. So and you can use that to eliminate solutions or create more solutions of your algorithms. And I think that's it's right now probably you're really confused if you're not if you're kind of new into quantum computing, but that's basically what the Hadamard gate is doing. So go ahead and play with these and with other combinations of gates. I think it's pretty interesting to get familiar with what the Hadamard gate does. So you can see that it does negate stuff when it's in a plus and minus, a positive and negative phases. If you do that on the other side, if you do that with a qubit that it's complex, it doesn't. So what it does is it makes the whole superposition complex. But pay attention, there is a minus in here. So I'm not so sure if I would now apply a Y gate, what would happen? Interesting. So the Y gate has moved everything. So now we've basically taken all our phase of both amplitudes is now it's now negative. Okay, interesting. If I apply Z gate, so combinations are pretty crazy. But that's basically what you do. So with the Hadamard gate, you create that type of uncertainty, and you have that negative effect on your phase of 1. So so it will turn your 1 from blue to yellow. But if it's already yellow, it will turn it into blue. So remember that circularity that we talked about in the previous videos. Good. I think that's it, and we probably kept that at the 10 minutes, which is really good. Perfect.